Hi, my name is Alan Phipps. I lead the MCU compiler team for Texas Instruments in Houston, Texas. And today I'm going to talk with you about how I extended LLVM source-based code coverage to support branch coverage. So source-based code coverage gives you a measurement for how thoroughly your code has been executed by tests. I mean, ideally, you want all of the code that you've added to have an associated test, and all paths through that code, you want them to be executed. Unexecuted code could have lurking defects in it, and the last thing you want is for a customer to run into those defects and only to determine that, hey, you never really tested this code. And so code coverage gives you a means to ensure that you're testing everything right and you're testing everything thoroughly. It can ensure that you have a lot more robust code. Code coverage is usually supported by various criteria, and LLVM supports 3. It'll give you function coverage, which will tell you how many functions in your code have been executed at least once. It'll give you line coverage, which will give you the total number of lines executed at least once. And it'll give you region coverage, which will tell you how many code statements in your code have been executed at least once. LLVM's source-based code coverage is called source-based because it's tied directly to the source code through the abstract syntax tree representation, which is a very accurate representation of the source code. So there are a few phases that are employed by Clang to ensure that code coverage is enabled and instrumented. The first thing it's going to do is it's going to allocate counters, and it's going to map those counters to regions in your source code. After it does that, it's going to instrument counters into the LLVM IR during the lowering phase. This is code then that you can then execute and run through your test infrastructure. And finally, with the data from the test execution, you can visualize that data using the LLVM Prof Data tool and the LLVM Cov utility. Conceptually, what happens during counter region mapping and instrumentation? Well, counters are instrumented by being inserted into basic blocks of generated code that's mapped directly to the source code. So if you look at this example, with our function foo here, Clang is going to add a counter to represent the parent region of the function here. I'm calling it counter 1. And this counter can be used to track function coverage. So this counter will increment if this function is executed. It can be used to track line coverage for line 10, which contains the if statement decision. It can tell us whether or not the if statement itself was executed. The second thing that Clang is going to do is it's going to add a counter to track how many times this right-hand side condition was executed. So I'll call it counter 2. It'll add a third counter to tell you how many times the then region of the if statement was executed. So within the scope of the then region, how many times was that region touched? And this can be used to track line coverage on line 11, for example. So if the return true is executed at least once, then counter 3 must be 1. Finally, to map the remainder of the function, Clang can use a counter expression. It can just use the difference between counter 1 and counter 3 to tell how many times lines 12 through 14 were executed. So it doesn't actually have to instrument a new counter here. It can just use a counter expression. Now, when you visualize it using the LLVM Cov utility, you'll get something that looks kind of like this. You'll see the line coverage shown in this count column here for every line in the function. And each, of course, line has an associated count. And there are also highlighted portions here. This y greater than 0 condition is highlighted. You can actually hover over this and get a count for how many times that condition was executed. And of course, the return true is highlighted in red here because its line coverage is 0. In fact, it was never executed. The text format looks very similar to the HTML format here. except that the region counts for the condition, the second condition here, are shown using this tick mark. And so this would tell us that the y greater than 0 condition was executed one time, according to this tick mark. Finally, LLVM Cov can give you a summary coverage report, which will tell you all of the various criteria of code coverage, function coverage, line coverage, and region coverage, and how well your code is covered according to those criteria. Now, one thing that's missing here is branch coverage, which is another level of granularity. I think branch coverage is very important. So the reason why it's important here is because we want to zoom in a little bit more on our example here. There are two conditions that make up this full if statement decision here. And if we're thinking about control flow, each one of these conditions creates a new path through this control flow. We know from the line coverage report in this example that the return true case, which is part of the then region of the if statement, was executed one time. But what was the execution path through the control flow that facilitated that? Well, by looking at the available coverage, you can kind of reason about that. We know that based on the region coverage by this tick mark here, that this second condition was executed once. And we know that in order for the then statement to be hit, both conditions in a logical AND operation must evaluate to true. So at least we know that much based on the available information. But it becomes a lot more complicated when you consider what the execution paths are around this control flow, and are you really testing those? For example, this line coverage information tells us that 3 times the if statement did not evaluate to true, and we ended up on line 13. Well, what was the execution path that facilitated that? Did the first condition evaluate to false? Did the second condition evaluate to false? Did both conditions evaluate to false? Well, again, using the region counts, you can try to reason about this, but it becomes really complicated really fast. It'd be nice if there was a mechanism in LLVM code coverage that would track this for you and tabulate it all for you. So that's what I added. Fundamentally, it comes down to if you can't be sure that all paths, if you can't be sure of what all paths in your code actually are, then you can't be sure that you're executing those paths. And that's a deficiency in your code coverage. It becomes even more difficult if you look at something like this, where you've still got 2 branch generating conditions here, but you have even less information available to you that you can use to determine whether or not you're covering those conditions. So branch coverage tells us all of this. It can tell us for every condition how many times was that condition taken or not taken. In other words, how many times did it evaluate to true and how many times did it evaluate to false. So I added this to LLVM source-based code coverage and extended the visualization to look something like this. Now, each condition in the if statement has an associated branch with it, and based on this information, you can determine how many times that condition evaluated to true or false. In other words, how many times was there a branch taken and a branch not taken? The text output looks very similar to the. Finally, I extended the coverage report to include branch coverage as an ultimate criterion that you can use to track your code coverage. And so, according to this, 5 out of 6 branches were covered. And sure enough, if you look at the code, there is one branch that wasn't covered, the true branch on the second condition of y greater than 0. So the ultimate goal behind all this is to allow you to ensure that you have 100% branch coverage. In other words, you want to make sure that all paths through the control flow of your function are being covered by a test. The C short circuit semantic behavior on logical operators makes this a little easier. In testing each condition, you will also test each if statement's decision. So for example, given our example here, we've got our if statement and the decision based on x greater than 0 and y greater than 0. So I want to ensure that the if statement evaluates to true and false both times, and I want to ensure that each condition evaluates to true and false at least once. Then the first thing I might do is write a test that passes in something 0. This would ensure that the initial condition evaluates to true, and it would ensure that the second condition evaluates to false, and the ultimate branch decision evaluates to false. That's simple enough. If I want to test the opposite case, if I want the first condition to be false and the second condition to be true, I might pass in this. This would ensure that the first condition would be false, but the C short circuit behavior on the logical AND operation would prevent the second condition from even being executed, and the ultimate condition would be false. So this means that in order to test that second condition, I've got to have a third test criterion here, where I can ensure that the first condition evaluates to true, and then I can ensure that the second condition evaluates to true. All of the conditions are tested here as evaluating to both true and false, and the result of the if statement's decision will evaluate to true and false. So this is complete. This is a very simple example. So how did I implement branch coverage? So recall the flow here. The first thing I had to do was kind of look at the counter to source region mapping and determine whether or not I needed to do anything special here. This happens when regions are created based on a walk of the abstract syntax tree representation in Clang. So Clang does have this notion of counter mapping region, which has this notion of region kind, which will tell you whether or not it's a generic code region or an expansion region, which is for macros, or another type of code region. And it's got an associated counter with it, which will track execution counts, and it's got line information here for the source code. So what I did is I added the notion of branch region to the region kind, and I wanted a branch region to represent a condition in the source code with two counters in it. One counter could be used to represent the true count, the number of times the condition evaluated to true, and another one could be used to evaluate the false count, the number of times it evaluated to false. So I could use the existing counter here for the true count, but I added a second counter here for the false count. Now, when all this gets encoded, it's encoded according to the branch region. So it encode two counters, and all the other region kinds will simply just encode one counter as they've always done. This ensures that it's backward compatible. Now, when looking at counters, I also had to ask a question, did I have to introduce any new counters to track branch coverage? I've already shown that instrumentation profile counters are already created for region mapping. And in fact, we can trivially reuse these counters to calculate branch condition counts. And just a reminder, a counter can also refer to an arithmetic expression between two counters, like an addition or subtraction between two counters. So if I have just a quick example here with a condition C in an if statement, Clang is going to add an initial counter here to represent the parent region that gets incremented prior to the if statement being hit. And it's going to add a counter to represent the then region of the if statement. So if I wanted to add a branch region for condition C, I could simply set its true counter to be counter 2 and its false counter to be an expression, basically the difference between counter 1 and counter 2. That would give me all the information that I need. So this is true for all control flow statements, actually. The counters are already there, so the data is basically already there. It just needs to be tied together. So what about instrumenting? Do I need to do something special here? Counter instrumentation in Clang happens when the abstract syntax trees are lowered to LLVM. Since I'm reusing the counters, I don't need any special instrumentation here. Well, there's one exception, and that's if I'm using logical operators. So to give you an example here, I've got a logical OR operation with two condition operands, C1 and C2. So like before, Clang is going to add a counter 1, and it'll be incremented before this Boolean expression is hit. Clang's going to add a counter2 counter, which will be incremented to show that it'll show how many times C2 has been executed. In other words, this counter2 maps to the right-hand side of the logical OR. And a key observation here is that it's the C short-circuit semantic behavior of the logical OR that facilitates this. So counter2 will only be incremented if, in fact, counter1 evaluated to false. If condition 1 evaluates to true, this will never be executed. So if I want to create a branch region for condition C1, I can map C1's false counter to counter 2, and the true counter is simply the difference between the parent region's counter and counter 2. But if I wanted to create a branch region for condition C2, I don't have enough information here to do that. I've got counter 2, which tells me how many times it's executed, but I don't have any information about how many times it evaluated to true or false. So I've got to instrument a new counter here to track C2's count. So I'll call this new counter counter 3. It's instrumented with the same semantic behavior as the logical OR so that I can achieve the same result. So in this case, I can use counter 3 to represent the false counter on condition 2, and I can use the difference between counter 2 and counter 3 for the true counter of condition 2. And of course, for logical AND, this whole thing is flipped a little bit, but the same principles apply. So the final thing I had to look at really was LLVM cov and what I had to do to extend LLVM cov to ensure that branch regions could be visualized. Now, LLVM cov is where the data is actually decoded and tied with the counters and statistics can be calculated based on that. Ultimately, what LLVM cov sees is, based on the initial source, it's going to see a list of code regions and branch regions, and it's going to sort them like this. So I've got a separate list containing the branch regions associated with this code section here. So if you recall from our example, there are 2 conditions in function foo. So I've got 2 branch regions for each of those, and then the various code regions. I might also have a macro definition that could also contain a condition. In this case, it does. And so I can have an expansion, a macro expansion that includes a code region, but also a branch region representing that condition. And also I might have a function that uses that macro. And so that's going to have its own code region and an expansion region that refers to this expansion for macro max. So ultimately what I want to do is take this information and display it. LLVM cov has this notion of subview that I extended to accomplish this. Subviews are demarcated, nested views in the source code that allow you to group like data together. And so I took all the branches. If the branches are on the same line, they're grouped together in the same subview. And subviews are also used to visualize macro expansions too. And you recall that macro expansions can be recursive because macros can reference other macros. So you can have subviews, nested subviews. And like I just showed, macro expansions can also have their own branch conditions. So this is an example here. I've got branch macro here, which is a macro expansion. It's used as a condition because it does in fact contain a condition. And so I've got a subview for the macro, which shows its original line number for its definition. And I've got a subview for the branch associated with that condition, the taken branch and the not taken branch. And in this case, you can see that even though this statement is executed 2 times, the condition evaluates to true twice, but the false sense of the condition is never executed at all. So it's 0. So the final thing I had to do in LLVM cov was add a branch coverage info class to extend the summary reporting. And this is just very simply to track the total number of branches and the number of branches that were executed at least once. So you can get a percentage for branch coverage. So given all of that, branch coverage was fairly straightforward to implement. There are some optimizations I'd like to go back and do in the future. Since I'm instrumenting additional counters for logical operators, I know that I can make better reuse of counters and eliminate redundant counters, especially in the case where I've got nested conditions like this example here. And so are we really making optimal use of the counters that are being added here? So I'd like to go back and clean that up. I'd also like to enable the HTML tooltip hover capability on source conditions so you can hover over the condition itself and get the number of times it evaluated a true and false, similar to what LLVM Code does with region coverage counts today. And I can include, I'd like to include better identification for special branch regions. For example, if you have a switch statement that has no explicit default case, Clang is going to introduce a default case implicitly for you, and that still represents a valid branch, and you'd like to represent that explicitly in the code, in your code coverage report. So I'd like to be able to identify that. Also, if you have constant folded conditions, it'd be nice to express whether or not that condition is always true or never true. So the ultimate goal here is to implement modified condition decision coverage, or MCDC. This is kind of the next level layer of code coverage built on top of branch coverage. And this usually involves emitting a truth table to confirm all possibilities of conditions to ensure that each condition independently affects the ultimate control flow decision. So before I close, I just wanted to note some observations here. So there are other vendors and other vendor tools that support branch coverage, obviously. One tool that's very well known and very well understood is GCC and GCov and LCov, which are its associated coverage visualization tools. So these tools will give you branch data. You see the HTML view here will give you a branch data column. In this case, the plus and the minus will indicate whether or not it's been executed, that branch has been executed. And you can hover over them to see the precise counts. And in the text view, it'll simply list out the associated branches and how many times they were taken, or if they weren't executed, it'll just be 0. The problem here is that with GCC, it's very difficult to tie the branches back to the source code. It's like they're kind of listed here following it, but you really don't have a designation for which branch goes with which condition. And you don't know which branch represents a taken branch or a true branch, and which branch represents a not taken branch or a false branch. And in other contexts, you'll see additional branches that aren't visible in the source code at all that really users have no control over. And other branches may be removed by an optimization. In fact, GCC advises that you disable optimization when using code coverage. This is not a problem in LLVM because the region creation is done before optimizations are run. So you get more precise data. In fact, just to show you again, the branch coverage that I added compared to GCC, we have an explicit indication of to which condition the branches map and which ones represent the true branch and which ones represent the false branch and what the associated counts are. So it's much more precise. So implementation is complete, and I'm in the process of upstreaming the work today. There is a Fabricator review, and you're welcome to have a look at it. The goal here is for branch coverage to be included with the stock LLVM source-based code coverage and supported on all the corresponding platforms. So in closing, I'd just like to thank you for listening to this talk. This project has been a lot of fun to work on, and I'd like to acknowledge some people here who helped me significantly with the design and allowed me to bounce my ideas off of them. Thank you very much.
Thank you, Alan, for a very interesting talk. I know how hard you work to provide this functionality in the compiler. We have a number of questions to ask today, first of which came in even before the talk. Is it possible to have 100% line region coverage, but not 100% branch coverage? And can you give us an example?
Thanks, Tim. Thanks for hosting the Q&A. So because of its level of granularity, 100% branch coverage must imply 100% region coverage. This is because if you're executing all branches through your function, through the control flow, then you're hitting all of the regions when you do that. And so it's not the case to have 100% region coverage, but not have 100% branch coverage. The line coverage question is slightly different because line coverage gives you a granular view. And so you could have 100% line coverage, but still not be hitting all the regions, for example, if a line has multiple regions. So, so the basic answer to this question is no, it's not possible to have that. 100% branch coverage should imply 100% region coverage.
Very good. Okay, so I have to admit this is my question because it interests me. What kind of bugs are you looking for, and what kind of bugs has your analysis found?
So the types of bugs that you find with branch coverage are issues with your conditions in your control flow that prevent your tests from really covering, all regions of your code. That's what it comes down to. You could have a bug in a condition or a bad condition that's not looking at the right data, and you might never figure that out until you've got a user who inputs something and then stumbles upon a bug, for example. So branch coverage is, because it's so granular, it's really useful in measuring all of the granular paths through your system. So at TI, we've developed this primarily to help other developers with functional safety code. So which is really important to make sure it's thoroughly validated and thoroughly tested. So that's why we've developed it at TI.
Okay, so sort of a related question. You're adding code in, and so I'd like you to speak to how much code expansion do you have, and related to that is what kind of systems is this an appropriate analysis tool?
So yeah, if by adding code you mean instrumenting, yeah, you're instrumenting code. You're adding the incrementing of counters and other tracking. And so you're going to get some code size growth, obviously. I don't have a precise measurement for how much that is, but that's the reason why with branch coverage, I wanted to take advantage of existing counters insofar as possible. Because we already instrument counters to track region coverage, we can use those same counters for branch coverage with the couple of exceptions that I pointed out in the talk. So, and as far as the system this is ideal for, I mean, if you've got code that has really complicated if statements, it can help you determine whether or not you're actually covering those if statements. But I think that the most important thing is it can help you write better tests that would help you write better code. And so maybe measuring branch coverage will then prompt you to simplify your if statements so that you can have more maintainable code and more testable code. And so functional safety system, like I mentioned before, would be one case where you'd want to do this. You'd want to kind of keep your code simple, easy to test, easy to write tests for.
Very good. Okay, so then can you compare or contrast instrumentation versus like instruction traces?
Sure. So it is possible, I mean, to derive coverage information from a simple instruction trace, and that would take less code overhead, obviously. And it would also wouldn't warrant any optimizations that you want to do. And I could see where that would be useful in some scenarios. However, it ceases to be really source-based at that point. I think when it's source-based, yeah, I think one advantage of having the source-based case is that it ties back directly to the source code.
Very good. Okay, so what kind of can you take this data and export it?
Yeah, so the LLVM coverage utility, LLVM Cov, has the ability to export coverage data into a JSON format, as well as LCOV format for if you want to use the GNU LCOV utility to visualize your code. And so I enable this for branch coverage as well. So the branch coverage data will be exportable to those formats too. So you can just export it to a JSON file and parse that if you want to derive a report, or you can export it to LCOV and use LCOV to visualize it if you want to do that.
Okay, and the user asks if that information can also be fed back into LLVM.
So at this point, no. It's not part of the profile guided optimization, for example. So it doesn't have, we don't have the ability to feed the branch data back in and use that to make decisions on how to optimize the code. But I will note that since we're basically reusing the region counters, and it is possible to do that with the region counters, you still get some level of information about how your code is executed. But if it's valuable to provide, the precise measurements for your branch coverage back into the LLVM flow to optimize further, that's something we could definitely look into if we could do that.
Okay, and so another user asked, what that information, what is turned on by default? What does the user expect to see? How hard is it to get your full coverage now?
So when this is fully upstreamed, the coverage summary information will be turned on by default. So the top level view across all of the files, you'll see the branch coverage information and the percentage of covered branches versus total branches. The file level view with the individual source level function view, I left that off by default, and there are just a couple of reasons for that. One is some people have flows that depend on what's currently output in the individual file level coverage report, and so I didn't want to all of a sudden start jamming additional information in there to make that more complicated. But you can turn it on with an option and get that information, obviously. The other part of that is when we enable better tooltip support, where you can hover over a condition and then see the counts. Once we do that, we could probably just turn it on by default in the file level view too.
Okay, so I have two more questions before we're going to run out of time, and this one is a fairly specific question. How feasible would it be to turn this on for example, vector predicates?
Well, it depends on how you're using vector predicates. So the source-based coverage is at the very high level. It's at the very high level in Clang. So it's basically tracking abstract syntax trees. And so, I guess it depends on the system. If at some point we turn that into a vector predicate or it's converted into a vector predicate, it would be possible to track that. But that optimization, if that's what's happening, that conversion would probably be inhibited by the presence of the instrumentation and so forth. I'd have to think more about some of the other details there. But if you had like a top level, representation or a vector predicate, I don't know. I don't know right now to think about that.
Very good. And finally, can you talk about ways in which folks may contribute to this project in the future?
Yeah, absolutely. I've given my email address in the slides. Please contact me. You can look me up on Fabricator. There are several things that we can do to improve branch coverage and new features that we can add on top of it, including the MCDC support that I mentioned in the slides.
Very good. So thanks very much, Alan, and thanks everyone for joining this session and submitting your questions. We encourage you to continue this conversation in the community board or in the roundtable sessions. Thanks very much.
Thanks, Tim.